My name is Navina Kumar, and today I'll be presenting about my poster entitled Doping Strategy in Biogas Fueled Solid Oxide Fuel Cells. So what is solid oxide fuel cell? Solid oxide fuel cell is an electrochemical device that produces electrical energy by oxidizing fuel. It is a fuel cell that operates at high temperature of a range of 600 degrees Celsius to 1000 degrees Celsius. It also has a high efficiency of 90% when used with combined heat and power. Solid oxide fuel cell has two major advantages, which first, it is a flexible fuel cell, and second, it is a fuel cell that can operate with other fuels, especially biogas. Why biogas? This is because Malaysia is known as the second highest country that produces the most amount of palm oil. So therefore, as we produce the most amount of palm oil, through this, a lot of waste such as palm oil meal effluent is also produced. And so therefore, there are abundant opportunities for Malaysia to convert this palm oil meal effluent to biogas. Doping is known as the introduction of a certain amount of catalyst into a pure metal. Doping of anode in solid oxide fuel cell has the ability to improve the electrochemical performance of the nickel-scandia stabilized zirconia cells that is used in this research. There are four major problem statements in this research. The first problem statement, it is that the use of a nickel in anode results in high carbon deposition that reduces the cell performance in terms of electrochemical performance. The second problem statement, it is that the occurrence of carbon deposition in anode is inevitable due to slow dry reformation of biogas. And third, it is the doping of catalysts in nickel-scandia stabilized zirconia cells accelerates the methane decomposition reaction, which contributes to an increase in the amount of carbon deposited in the cell. And lastly, studies on the most optimal catalyst with biogas is still in its early stages and thus requires in-depth studies to achieve high-performance solid oxide fuel cells. There are three major objectives in this research. The first objective, it is that to produce new nickel-scandia stabilized zirconia anodes through surface impregnation doping method that has improved tolerance towards biogas fuel. Second, it is to determine the effects of four dopants, copper, cobalt, samarium, and tin on the anode's microstructure through scanning electron microscope (SEM). And lastly, it is to evaluate the carbon deposition and electrochemical performance of nickel-scandia stabilized zirconia cells that have been doped by four different catalysts. So the methodology first starts off by pellet pressing of scandia stabilized zirconia powder into button pellet shapes. These pellets are then sintered at a temperature of 1400 degrees Celsius for a duration of 6 hours. Once the pellet has been sintered, it goes through a process called screen printing process, where anode, cathode, and buffer layer is screen printed onto the pellets. Once the pellet has been screen printed, it goes through the sintering process again. And then it moves on to the doping process, where surface impregnation doping method is used. Is used to dope catalysts of copper, cobalt, samarium, and tin. And then it is calcined at temperature according to the dopant used. Once the pellet has been calcined, analysis such as maximum power density, electrochemical performance, open circuit voltage, carbon deposition, and microstructure of the anode is analyzed. So the results obtained are in terms of porosity and carbon deposition. So figure 1 shows the SEM images of carbon deposition and porosity of A, which is copper doped, B, cobalt doped, C, samarium doped, and D, tin doped. It can be observed that figure B and D shows that it is more porous compared to figure A and C, as it is doped with different catalysts but with the same amount of dopant for each sample. It can be concluded that doping of a certain catalyst has improved the electrochemical performance of and reduced the amount of carbon deposited onto the solid oxide fuel cells. And lastly, I would love to acknowledge my supervisor, postdoc staff, and also Institute Self-Fuel UKM, as well as Kementerian Pengajian Tinggi Malaysia and KRIM UKM. So that is all from me. Thank you.